So we'll go ahead and get started. This is Splashcast episode 6 of Standard Fluids. Today I'm joined by John Owens, our principal advisor for chemical engineering, chemistry, with a long history past at 3M, and a very close relationship with our other advisor and previous podcast guest, Paul Rivers. Lots of stories shared between the two of them. As well as Kelvin Cabrera, who's our international operations director, and currently between both fire protection as well as our engineered fluids. And so today we're going to do a little bit of a deep dive. We're going to try to get into some chemistry, try to give some interesting science for those of you listening. And we're going to talk about the past stories and experiences that both John and Kelvin share around the problem solving and the development of the chemistry that we at Standard Fluids currently sell, and the history behind its development at 3M, and where Kelvin out in the field brought in experiences or lessons or challenges from customers, and where John Owens was in the lab developing these solutions and these products. And talk about how we're still doing that at Standard Fluids. So to get right into it, I want to first get some of your background and hear maybe a few things that you like to emphasize about your career, John, and your career at 3M, a little bit about what you do now. And I'd love to hear how you got into chemistry, chemical engineering, and maybe one of your first earliest memories that was really like, man, this stuff is cool, and this is why I'm going to make my life and career better.
Boy, you asked me to go back a long time, Nolan.
Yeah, yeah.
Yeah, I mean, my interest was just chemistry in general, because I found it an interesting topic, and chemical engineering in particular because it was a way to apply math to it as well. So a
Yeah.
chemical engineer is a little bit like a chemist that doesn't mind doing math, um, which not all chemists like. It's more of like a physical chemist, maybe.
Yeah.
Yeah, so I spent 39 years at 3M Company. Most of it was involved in organofluorine chemistry research and product development. A lot of the products that came out of that effort are what Standard Fluids sells today. Um, so I had worked in with a big project team, really. It wasn't all myself by any means, but a big project team developing, researching these compounds through a lot of we did some modeling work, but also mostly hands-on chemistry of you have to synthesize the material and evaluate its properties. You learn as you go, and to be honest with you, you learn just as much from failures as you do successes.
Yeah.
But you start building knowledge along different chemistry classes and understand which direction takes you where you need to go to solve what industry is looking for. So I had done a lot of the work at not only with the synthetic chemists to come up with, hey, what molecule do we want to make? What do we think would help solve that problem? But then evaluating the properties of these new compounds as they're synthesized. And then one of the areas that I really focus on too is looking at their environmental fate. Hey, eventually some of the stuff could leak into the environment after the end customer uses it. What happens to it? Because ultimately, all of these products were trying to help solve some environmental problem. A lot of the initial impetus for this came from materials that were ozone depleting. Now, the areas I worked at, they didn't make or sell materials like that, but it was viewed as being an opportunity to come up with replacements.
Yeah.
And so finding non-ozone depleting compounds that could still meet the performance and safety requirements for this industry was the initial part of the effort. But eventually it also then morphed into looking at things that could be less impact on climate change. Because a lot of the early types of compounds that came out to replace ozone depleting chemicals, they solved the ozone depletion issue. They would be non-ozone depleting, but they were eventually found to be potent greenhouse gases.
Oh,
And so it's sort of like trading one problem off for another. And that wasn't intentional, but that's just how the chemistry ended up working out.
yeah.
I mean, it's the same thing with the original ozone depleting chemicals, CFCs, halons. they were kind of viewed as being, really miraculous chemicals when they were first introduced many decades ago. And it wasn't until long after they had started being used that it was determined that, hey, these materials actually survive transport through the atmosphere when they're emitted. They pass through the lower atmosphere, well, that's the troposphere. They make it all the way up to the stratosphere, which is the next layer of the atmosphere, and that's right where naturally occurring ozone is at its highest concentration. And that's where it does its job to help protect UV low wavelength UV light from reaching ground level and protecting the Earth from the damaging effects of UV radiation. In some ways, if you could have designed them worse, but
Yeah,
again,
right.
when they first were coming out in the 1940s and 50s, that wasn't known.
Yeah,
It wasn't
yeah,
even studied really to any large extent. That understanding didn't come out until the 70s. By the time then those started to get phased out by the late 80s to about the very early 90s is when the group I was involved with realized, hey, we have an opportunity to maybe make some materials to replace those kinds of
yeah,
compounds.
yeah. It's very interesting because like um, it's the layers or the stages of evolution, right, in science, right, where it was something that, hey, we've got an opportunity to create better performing products. We created those better performing products, and then the inverse side of the science said, hey, we have better ways of measuring environmental impact, and now we're seeing that these products are having a detriment on the environment. So then it flips
Right.
again and says, how do we develop these better performing products to alleviate some of those problems? And it starts kind of getting into that cycle. The exciting thing is through the work that you did and a lot of the research and development and the modeling, bearing in mind some of those problems, have left us with the products that we have today. Right. And as the science continues to evolve and we start to be able to measure environmental impact, that's ultimately what's led us to the products that we still sell today, and we still stand behind them and their environmental impact. As you know, they are the best performing and provide the lowest environmental impact. Respective to each product, they all have various levels, but I think this is the introduction into where the customer side of things really starts to come into place. And so, Kelvin, I would love to hear a little bit about some of your early stories. I know that you were involved in some of the pharmaceutical and some of the medical industries that stood to benefit from this newly developed chemistry. And I'd love to hear
Sure.
about maybe an example that one of these customers you met with, or they came to you and said, hey, I've got this challenge. How do I do this better? And then I'd love to hear some of John's background about that product and maybe how that product came to be.
Sure thing. Thanks, Nolan, and good to see you again, John. Really good. So I'll tell you a little bit of a story. Back in 2009, when I joined 3M, I joined 3M because I'm an electrical engineer, and I was dead into the center of working with telecommunications. But my background in pharmaceutical business, as you mentioned, a medical device, my manager, she told me, hey, I need you to help me understand these products. They're called Novak from 3M, and I need you to help me with it. And I started reading, and I got so hooked in and engaged into what could be done, and that I just fell in love with it. That's when the team from the States, I remember Pete Aiello and Lester Sandy, they came back to Puerto Rico and helped me engage in the market, and I started learning, and I mean I really enjoyed it. So there comes a time this electrical products manufacturing company called 3M, because they wanted to reduce their waste emission from their manufacturing, because they had a very dirty process, and they came to us asking for help. Can you guys help us with 3M expertise? So that was one of my first experiences, and it was actually they were doing injection molding at the time, and the process was really they use a lot of water and different kinds of so to simplify detergents, I would say, which were aqueous in nature, and all that with the contaminants that they used to spray the molds and to clean the molds. that would all become hazardous waste.
Yeah.
So they had to take particular care of that. Then they had to do all the processing and all the documentation to properly dispose of these contaminants. So I studied the situation. I engaged with the 3M team in US, and they told me, hey, use a 72 DE product to clean the molds, and use maybe uh, the um, the I remember at that time we had the aerosols. Use the aerosols, the contact cleaner lubricant to spray them all. That way, it will detach faster. You would get less dirty. Hey, we tried it. The molds, all the casings, all the injection molding, all the injection molding molds, they came off clean. We generated less pollutants, and when we cleaned them with the 72 DE, it would all evaporate. We would just left with a dirty rag and some dust, and that was not considered, in between, in the midst of that scenario, it was not considered a hazardous waste because of what, how things happen.
Hmm.
And we helped that company save thousands of dollars in waste management, thousands of dollars in man hours of documentation, all
Yeah.
because they opened up their doors to implement it, and they eliminated water usage from their cleaning facilities, which is, I mean, we're all used to use water for cleaning, but it's actually a very valuable resource, and that's something that we learn to explain and teach our customers. Hey, you're used to wasting water. You're used to in your process. You're used to post treating water because it's so dirty. You have to treat it to then
Yeah.
being able to uh,
Right.
going back into all the city water system, and that's a huge expense. And with the induction of our products and our science, you can alleviate that. And at first, it was seen as, wow, your products are really expensive. But when you look at the whole process, the total cost of ownership, it just brought the plant. I mean, we cleaned faster, we cleaned cleaner, less contaminations, and the overall process was improved. And I mean, that was one of my first experiences, which I truly loved, because I mean, it was really engaging, and that get me going. Wow, what else can we do with this?
Yeah.
So that's one
So
story.
yeah. So John, he mentioned 72 DE as well as some of the contact cleaner stuff. Do you have any stories from the development of those products?
Yeah, so early on in our development efforts, we'd created sort of a couple of key base molecules, hydrofluoroethers. Um, that's a basis for both of those products you just mentioned. Um, they're really useful materials. They're really safe materials. They're not flammable. They're low in toxicity, but they can be a little limited in terms of the areas they would be applicable for in industry because they have somewhat limited solubility characteristics.
Hmm.
There's only certain hydrocarbon or organic materials that are going to want to dissolve in a material like that because it's so highly fluorinated. That's what makes it so low in toxicity and so non-flammable. But then it limits your ability to tackle these kind of applications like Kelvin just mentioned.
Yeah.
So what we started to do was, well, look at how can we augment that solubility characteristic? How could we broaden the reach of those compounds by blending them with other components that could be just as safe, low in toxicity, but on their own might be flammable. So you would never use them independently to do solve
Yeah.
this because now you create a huge flammability or fire hazard. We were able to make some mixtures with the hydrofluoroethers, and so I'll get a little nerdy here for you.
Of course.
They're
Yeah.
azeotropic mixtures because an azeotropic mixture means they can't be separated by boiling. So when you mix two common solvents, more often than not, that what's going to happen is if you mix those together and now you boil that mixture, the lower boiling component, the one that's more volatile, is going to get enriched in the vapor phase. So the longer you keep boiling that and then condensing that vapor, you're stripping that lower boiling component out of the liquid phase. You're changing its composition. Well, you don't
Yeah.
want that to happen in an industrial operation. You want consistency. So for example, if that lower boiling component were the one that keeps the mixture non-flammable, well, now your mixture might become flammable if you strip that
Right.
out.
Yeah. Yeah.
So you have to make certain you can maintain the composition throughout the working conditions for that particular application. So we had identified a number of components that we're able to form these azeotropic mixtures with, based off of that hydrofluoroether molecule and form a material like this.
Wow. And so you said the kind of the boiling component of it. Was there particular metrics that you were going after as far as the boiling point, right? Because I would imagine there's kind of a sliding scale depending on how some of these interact. Some may boil at a low temperature, others are going to boil at maybe a higher temperature. Was there any kind of development that posed a challenge there of trying to find one that could maybe apply to a broad category of industrial environments that was best, or did it come down to only maybe a couple of them for specific temperature environments?
Well, in a lot of cases, maybe not in the particular one Kelvin just mentioned, but a lot of cases they had used a previous chemical or mixture already. And so
Yeah,
we'd often be trying to find mixtures that could sort of replicate those same kind of boiling ranges that the industry was already used to. In the
yeah,
case of where Kelvin mentioned we were maybe replacing an aqueous process, that's different.
yeah,
Hmm.
Because they probably weren't literally boiling it in an aqueous process, but
yeah,
with a solvent they might have. Yeah.
yeah,
To mention an example of what you're talking, John, there was another instance where I was working with a cleaning process where they were using an HFC, the one that's also used Freon. They were using Freon. That's a CFC, right?
So if it's actually Freon, the old trade name, that's actually a CFC, a chlorofluorocarbon.
CFC. Yeah. So they were using Freon to do some cleaning of some parts. That was in the west side of the island, and we ended up using HFE 71 IPA, and it was fun because I mean, talking about the azeotropic blends, and I'm not a major in chemistry as I
yeah,
mentioned, but I learned the terms. So when I presented the product and I showed that it had alcohol in it, so but that's flammable. I said no, that gave me the point to explain how the azeotropic blends work, and it was so beautiful because I mean, when you teach people and they learn and you see their eyes expand like wow, you can really do this. And I mean, the part was really sensitive, so it had some nylon and some polyester blend, so we could not use a stronger agent like the 72DE because it would damage the plastics, so we used a lighter version which was 71 IPA, and it just worked beautifully. So in this case, and this is something I want to bring out, that I mean, one of the major things that we do is, as John mentioned in the beginning, you need high performance, safe for the environment and safe for the people, right? So some instances you work again, in pro of getting the process safer or more sustainable, but we were able to do all of that in a single shot. Why? Because we took care of all that. I call it that pyramid of performance. I mean, that was something that I invented back in the day. I just mentioned it, just occurred to me, and it worked so well because I mean, it was safe. I mean, using the 71 IPA, we could clean it well. It was safe for the people. It was safe for the environment, and we helped that other process improve a lot, a lot.
yeah,
Yeah, Kelvin, we often, would call that the balance of properties. That
There.
you're trying to solve this environmental concern, but you didn't want to sacrifice performance or safety aspects.
Exactly, exactly. There was I mean, sometimes a lot of times you had to do well before these molecules. You would have to either have it work well and be good with the environment, or have it work well and be safe for the people. And we could do that balance. So that was really. I mean, that's mostly how we solve things. I mean, it was just solving that big problem with just one product, a lot of testing, and providing a solution. It was really enjoyable. Many years.
yeah.
Yeah.
Yeah, no, I think it's really cool to see when I first came into this sort of realm of things. My background's in the fire industry and everything. I was very fascinated by the 1230 product and what it was able to do. Right, it really does on paper seem like this wonder chemical that it does everything right, and as I've continued to learn more and I've worked closer with Steve and likewise you, Kelvin, to start to understand how, and John kind of talked on it a little bit. I would love to maybe, I think this is where I kind of want to understand maybe a deeper level of it. We have these like sort of base foundational chemistries, right, that were developed for a particular application. But then, like you mentioned, there were specific applications that someone was trying to come up with something that there was a level of interaction that didn't necessarily work for maybe what the base product was, but you were able to identify ways that you could take the product or a similar behaving product of what the customer is used to using and blend it with these sort of foundational products. What is good to know about for some of the foundational products, and then what was the engineering process, right? We'll get into maybe a little bit of that math side of things. What was the engineering process to say, all right, here is this foundational product, and here is the problem that we're solving. How do we attach those two, right? Like you said, I want to understand a little bit of the chemistry about it. Feel free to get as microscopic as you want, because again, I think it's interesting stuff.
Yeah. So in a lot of cases, when we wanted to make a mixture or a blend of materials, so one of the base chemicals that we had created, like the hydrofluoroether, with another organic solvent to try to supplement its properties. We had some targets we wanted to go after in terms of what kind of solvent characteristics did it need for the end product, what kind of boiling point did it need. But then we had to do kind of a real extensive search for materials, both, in terms of trying to do some modeling and then just a lot of hands-on experimentation, because you don't get to pick where the azeotrope forms. Nature does. It's a thermodynamically non-ideal mixture. Say that 3 times fast.
Yeah.
That in a lot of cases here for these materials are going to form a minimum boiling mixture. So if you think of two common solvents that you're going to mix together, one, product A has a boiling point of X, product B is maybe pick a number, it's 2X, and there's going to be some line in between. If you make a mixture, it's going to fall somewhere in between there when you make a mixture of those two components. With an azeotrope, this type, and it's a more common, you couldn't get a maximum boiling one, but that's usually a whole different kinds of materials. These kind of materials you mix to organic solvents, it's going to make a minimum boiling azeotrope. It actually goes through a minimum of the curve. That azeotropic mixture boils at a boiling point that's lower than either the two individual components would be on their own. And you don't get to pick where that's going to occur. Like I say, nature's going to pick that for you. So it takes a lot of hands-on experimentation to finally find or identify the right kind of mixture to solve some of those problems.
Yeah. And I would assume that comes with lots of what I've referred to, or I've heard people refer to as like cup burner tests, right? So you're essentially putting it under flame or in temperature to see how it behaves.
Kind of, yeah. In that case, cup burner is different because you're actually trying to find out what's the extinguishing concentration for an extinguishing agent for a given fuel that's the hazard. In this case, we actually would automate a lot of testing to be able to, you're boiling one component, you're going to add another component to it. Does it go through a minimum or not? And if it does, then really analyze it more precisely to find out exactly where that minimum occurs. And then to complicate matters, that minimum boiling point, that'll change depending on what the pressure is.
Okay.
Exactly. Of course.
Another thing that nature is going to determine. Right? Yeah. Interesting. And so I would assume there were probably some circumstances where you were, well, it's science, right? So you would know if something being put together would become an azeotrope, or would you have to put it through the testing and sometimes it would come out and it wouldn't hit that minimum. It might have that linear connection.
Oh, that would happen all the time. Yeah.
Okay. Yeah.
But we also would come up with ways to try to do some prediction ahead of time, at the very least to say, well, if an azeotrope did occur, what kind of concentration could it possibly be in? Based upon all the data that we had already developed, you can start to make some predictions of it.
Yeah. The math of the engineering, right? I suppose. Yeah. So Kelvin, in some of these applications, I know you continue to work with customers that utilize these blends and everything. What are some current examples, right? We still have some customers that we're coming across that maybe are or have used these blends or maybe used a type of blend in the past or are looking to move to blends. What are some of those customers that you can talk about that have some of these really kind of unique applications that, like I said before, maybe a foundational, a base chemistry, it doesn't suffice and we need to have these blends in place for it?
It's something that's really it's always interesting and has not changed much. And I always remember in the presentation, we had about 10 points to consider when doing a cleaning assessment.
Mm.
What is the surface? What are we cleaning? What are the limitations? What are the expectations, right? So
Yeah.
so we would use like a compatibility matrix on what do we have as the materials or the substance that we're using. What are we using? What are the expectations of it? What are the materials that how clean do we want it? And and from there, well, of course, with history and a lot of examples, you could get, you know, more or less where would you use it, right? Um, Likewise, a lot of the one of the processes that I liked a lot was the process of coatings.
Mm.
Blending some silicone, which doesn't blend with barely, many things. Then you would blend the silicone with our agents, so you can dip the part, and then you will get, a really, I would say, nanometrically thin layer of silicone that would actually help that part, be lubricated for better functioning. And you would use that, for example, in the electronics industry. But that same thing, that same principle could apply for the medical device industry. So there were many applications where for you would use like the same concept of processes, but for different industries. That said, through what has happened throughout the years or the decades, I should say. In the beginning, there was a lot of usage of chemicals. Then, came the oh no, let's use water, and the trend of the water and the aqueous processes, and everything was aqueous. Then came the time of cleaning with vapor degreasers, which is a smaller, you know, sink size appliance that helps you accelerate and do really in-depth cleaning of the processes. And then the technology switched to that. When 3M left the market, everybody was, confounded, and now everybody switched, in the past years, everybody switched back to the aqueous solutions, even though they had their issues. Because water is not the perfect, cleaner for a lot of things, and
Right.
and it leaves a lot of residues, and there's, a whole lot of complex items afterwards,
And
and
the
it could take
potential for
longer.
corrosion, Kelvin. And one thing
Exactly.
we'd worked on some drying products many decades ago. Often, even if the water or aqueous or semi-aqueous process could actually clean the component, they would have a hard time drying it. Especially if you have
Interesting.
Or
real
corroding
small
it
interstitial
post-word. It was just, yeah,
spaces, trying to get water that has, very high surface tension, get that out of there, it's extremely challenging. So that's why in a lot of cases a low surface tension solvent is a much better solution.
Yeah, I
exactly.
was going to say, it seems like a lot of the blends, a lot of it was cleaning based, or cleaning applications is what came up a lot. But
Hmm.
um, like Kelvin said, there's other uses where it's used as an application agent or of some
To
kind.
deposit a coating, yeah.
Yeah,
To
yeah,
deposit the coding, yeah,
Yeah, which I think
and
coating is sort of almost like the exact opposite of cleaning in a way, right?
yeah,
exactly,
So
yeah.
if it can do one thing, and it can often do some of those other things too.
yeah. And so, I guess again, this is my maybe probably wrong simplification of it, but it's these chemicals, these products stand as a sort of a translation agent, right? It's either it's cleaning, it's removing something from a surface, or it's helping apply something to a surface.
Hmm.
At the end, the goal is to leave only that thing you want there, or leave the thing you don't want there. To allow
And
it to
remove
be
it properly.
yeah, cleaned or applied, but do it environmentally friendly, low or no toxicity, safe for people to use, because cleaning and application processes are typically very hands-on or have lots of interaction to them,
Yes.
and everything. And I think it shows that the science and the chemistry of these has kept up with the continued changes to environmental. I don't want to say environmental scrutiny, but I guess the environmental science, or the environmental consciousness of industries, right? As industries continue to look at improving, health of employees, employee safety, but also the environments that they're in. Kelvin, you live and worked in Puerto Rico your whole life, and so you have a beautiful environment there that obviously the industries want to be able to protect and keep clean. I would love to hear, because John, in your consulting work, I know you work with and work in parallel to some governing bodies that oversee, environmental discussion around some of these products and the continued evolution of these products. Maybe I would love to get a good, again, a scientific explanation about what is it about these products and what do we see moving forward that lends itself that these are still the environmentally and human safe products that continue to be applied, and how we at Standard Fluids have this expertise to help our customers understand some of the background about this, but know that it's not on them to have to worry about it. We have the expertise and are there in their corner to help them with it.
Yeah, let me tell you a short story of something that I did, and
Yep.
and then I'll let John do the science stuff because it's way more interesting. But I always remember once, and I think I've told you this offline, Nolan. I had many years ago. I had a meeting with one of the United Nations Environmental Program particulars, some director. I think it was Panama or Costa Rica, and I had the chance to explain to them. I quantified how much, how many conversions I had done in the past from either HFCs or CFCs and such, and from the fire side, likewise, how many thousands of pounds had I been able to transfer, and then I put the equivalent of that using the EPA equivalences calculator for the greenhouse gases. And it turned out to be, I think, thousands or millions of pounds of equivalent carbon emissions, avoided by switching to the products, right? And when I gave them that number in the last, I told them in the last 6 years, I've been able to do this massive offset number.
Yeah.
And they were just like, wow, that is a lot. And I said, yeah, and that's and I told him, I've done that twice. Yeah, I told him and her in different countries, and that is what we're trying to push. That is what we're trying to push. And the way to do it, well, John can explain it better than me, of course. But yeah, it's really impactful what we can do. It's still really relevant on what we're doing today. And as you mentioned before, we are here to help you raise the standard, bring stuff back, bring processes back to where we should. Why? Because the team is back. The same people who created the molecules are here to support, and we are here once again to set things straight again and raise the level of performance on cleaning, fire suppression, and all the different applications that we have worked throughout the years in a highly technical scenario. I'll leave John to talk more about the environmental aspect of that.
Yeah, I think so. And it's kind of goes back to what we talked about a little earlier. It's sort of that balance of properties, right? That you knew you needed to solve an environmental challenge, but you didn't want to sacrifice the performance or the safety.
Right.
And to be honest with you, the product development team often kind of treated the environmental agencies like a customer as well. What are their expectations to try to look down the road what was going to be expected of chemicals so that the end customer could avoid having to keep continually switching one product after another every time one is found to have a problem. So you're trying to leapfrog that and avoid any future issues. Like I say, from an ozone depletion standpoint, that was colleagues would probably be upset with if I said it was easy to solve, because I'm sure a lot of industries didn't think that. But primarily, it came down to avoiding certain detrimental halogens in the molecule, like chlorine and bromine, because those are what end up really depleting stratospheric ozone when the compounds are emitted to the environment. So without those, that's generally not going to make an ozone-depleting compound. The challenge came, how do you make something that's not going to end up being a pretty strong greenhouse gas? Because the reality is every organic molecule that gets into the atmosphere when it's emitted, it's going to absorb some infrared radiation. They can't avoid it. It's just inherent in those kind of molecules. But if they stay in the atmosphere for a long time, then they're going to have what's called a high global warming potential, meaning they have a potential to have a much stronger contribution to climate change. So how do you avoid that? Well, you have to find a material that's going to actually break down much more rapidly in the natural environment, in the natural atmosphere, so that you have
Yeah.
a short atmospheric lifetime. And that's what really was the key to designing a lot of these base molecules.
Yeah, I like that you mentioned that you on the laboratory development and testing side of things, you not only had the end paying customers as a customer, you had the environmental organizations as a customer, right?
We,
And
we used to say EPA is a key customer.
yeah, yeah, no,
Yep,
it's
yep.
it in some cases it's the make or break customer, right? And
Oh yeah, because they don't have to approve the chemical. It goes through an extensive process before you're ever allowed to put it into commerce.
yeah,
Looking at not only environmental properties but also toxicological properties. How safe is it for workers to use?
right.
What are the risks involved, basically? Yeah, and they could say no, it's prohibited.
Yeah. And it's not, it takes a lot of time and dedicated resources to be able to maintain, it's not just developing the product and bringing it to them and, green light or red light it. There's a continued discussion of the continued evolution, what they're looking at for these things, right? Like you
What are
said,
they looking for exactly? Yeah.
yeah, it's not just all right, what's going to change in the next 5 years. It's what trends are they looking at and where do they expect
Long
those
term.
targets to be in 10 to 20 years, to be able to provide that confidence that it not only gives a green light, but it gives them a good degree of confidence of what this product is going to be able to do. Last thing they want to be doing is reevaluating a product every 5 years as it continues to come out and new products that beat or meet the requirements that they set at their regular intervals for things. And like you said, Kelvin, that has allowed for a not just a minute change in measurable environmental impact, but in some cases leaps and bounds of environmental change and the measurable impact that it has on ozone depletion potential or the greenhouse gases, the measurable greenhouse gases that come off of the products. And
And or the
yeah,
excessive usage of water resources, which a
yeah,
lot of people just go, don't mind because they're used to do it, but it's just wasted water, which
yeah.
it gets contaminated.
Yeah,
So
in one way, shape, or form, every one of the products we sell replaces a water application or a water use of what it does. And like you said, that's a key thing of being able to change the waste byproduct that a lot of the industries that we serve were dealing with before. Again, my background's in fire. It's replacing the large amount of water usage that can come with fire protection is huge and has a huge impact on those things.
Or sometimes completely inappropriate because in general, energized electronics and water don't typically mix well.
Yeah, yeah,
nope, nope.
exactly. And again, the human factor of things, right? It's how much do you want to put a gas, a high toxicity gas, into a space that could have people around it, right? And being able to make sure that you have products that are safe for people to be around. So what kind of and this can go back, several years in time, but maybe some of the conversations or lessons that were learned in conversations with environmental agencies that still stand today about a product that was developed, the conversation or the approval by those agencies of the product, and one of the things that Paul kind of always mentions was he was always waiting for the shoe to drop on 1230, right? He was always waiting for something to come up that was like, oh, there it is. That's the final factor, and now everyone's going to move away. They're going to try to find something different, and it never came, right? The 1230 product is still replacing environmental products that are have phased out or are phasing out. What kind of things, what backgrounds can you share on that?
I mean, a lot of areas aren't even researched for those kinds of alternatives. I mean, halon in the U.S. and other developed countries, it was phased out. I think it was the end of 1993 was the end
Yeah,
of production. So it couldn't be produced any longer. If you have it, you can still use it,
Yeah.
So there's still some out there. Airline industries, most aircraft engines are still protected with halon, things like
Mhm.
that. But the supply is dwindling because it doesn't get made anymore.
Yeah.
So um, in those intervening decades, not just years, but decades,
Yeah.
thousands upon thousands of compounds have been studied to look for
Yeah.
alternatives. Uh, the 1230 molecule you mentioned, which is a fluoroketone, it kind of found the sweet spot between that balance of properties between performance, environmental, and safety attributes.
Mhm.
Now, I don't want to say nothing could ever be invented
Right.
that's better, but you might have to identify a new element.
Yeah.
Yeah, I mean, for years, Nolan, we talked to the lab. What's next? What's next? What's the next 1230? What's the next 1230? And I don't know if it was John one time or somebody said in the conference, guys, we have tested over, so many, I think it was hundreds of molecules since it was invented. And yet, we have not reached to that, as you mentioned, that sweet spot.
Yeah.
And I think not yet, right? No, John? I
Yeah, like I
mean,
said, there's so much research has been done, not only by, the chemical industry itself that would make a product, but by, universities, government laboratories, and literally for decades. Um, there's not a lot of the periodic table that hasn't been investigated
Yeah.
to be able to
Yeah.
make a molecule to do some of these kinds of things.
Um,
So again, never say never. It's
yeah. Yeah.
yeah, I mean,
but
but
it's the likelihood of a new one being developed that is yet even better gets smaller and smaller each passing year.
Yeah. Well, and it like you said, um, innovation is an unstoppable force, right? There is always going to be innovation and something new that comes out. New may not always mean better, but there might always be something new. But we in credit to you have great products that are hugely impactful, hugely beneficial to the customers that we serve, and the research and testing and the continued effort to innovate. Right? It's like Kelvin said. Just because 1230 was created and it had a strong impact in the market didn't mean that there was well, what else can we do, right? There was continued attempts to evolve and see what changes were out there, and we still have this product, which is a testament to it, and all the other products that we have. It shows the amount of time and effort that went into these, and the continued attempts to innovate new things. And I
and
think it's worth kind of talking about how um, our product portfolio, as it stands, is it's not going to, like you said, we're not going to develop a new element anytime soon that's going to broadly expand our catalog or portfolio of products. But we still get the enjoyment of new industrial challenges that may come out with the innovation of new technologies. The rise of data centers and the increased demand on systems lends itself to new innovation and new cooling methods that we are able to offer. And this is where our team really starts to kind of come in and show the expertise. Kelvin, what do you have
yeah,
to say?
one thing that I wanted John to expand on what we're talking here is something that we've heard all of our lives, but a lot of people need to know. I mean, we are a new era where there was a time where we were the only ones who were manufacturing the agents,
Mhm.
and now we've come to a time that a lot of people are manufacturing may be manufacturing HFEs or fluoroketones or any other chemical. And I wanted John to expand on how critical and how key is to be able to take care of the quality and the quality assurance processes. How key is this to the proper functioning of these chemicals that we're using? It's not just making for a ketone or an HFE. It's how you make it and how critical is it to have the correct quality of agent or chemical manufactured. Because I think that's something that needs to be explained in detail, and I think that's one of the things where we as Standard Fluids and have have excelled, and that's the reason why our company was formed in terms of making sure that we have the right level and the high level of manufacturing that is needed for the industry.
Yeah, it's great point, Kelvin. Yeah, John, whatever.
Yeah, I think that is a unique aspect for Standard Fluids, is to have a number of us involved that were directly involved in the development of all these different molecules. Um, like Kelvin said, there are other companies I know manufacturing and selling the exact same compound or something very similar, because all those patents had long expired. Um, but they don't have that same level of experience with the development that a lot of us have had. I've told this story a number of times. I don't remember if I've told Nolan this. We we did evaluate a product uh, that was from a competitor, and actually it was supposed to be 1230, or a a knockoff of that. It was supposed to be the exact same compound. Turned out it wasn't even the same chemical. Um, Number of steps in the process to make it, and somehow they missed the last step. And unfortunately, these intermediate chemicals look physically the same. They're still a clear, colorless liquid. They have almost the same boiling point. A lot of physical characteristics are the same, but they don't have the same low toxicity. They don't have the same advantageous environmental properties. In the case of fire protection, they're not approved to be put into a fire protection system because there's a long process to get those approved. And that's, something you miss if you don't have some of that expertise from all the product development that Standard Fluids has.
Yeah. No, and Kelvin, a great point to bring up, and a perfect anecdote to add, John, where the continued testing and validation of these products is needed.
The right product at the right purity. Yeah.
Yeah, and it's not as simple, like you said. There's steps in the process. It's not as simple as turning on the manufacturing process and you're going to get the exact same thing every time. You're dealing with compounds that are naturally occurring. There's going to be slight variations in those things, so it's going to come out with a little slight variation here and there. It takes one small change. One of the things that we talk a lot about is the humidity or temperature in the environments that they may be produced in, and how it may affect the moisture content of something, right? And it doesn't necessarily change the performance or the toxicity of it, but it then could interact with something different. A fire system is put into a steel cylinder that you don't want moisture in, because that can start to negatively impact the system or the cylinder that it might be in. And so the continued testing and validation of quality is key, especially like you said, these patents expired, years ago, almost, it was 6 years ago now. We're a little bit around there, which doesn't feel like it was that long ago. And so now that you have, various global manufacturing, at Standard Fluids, we go through the effort with the chemists and chemical engineers that develop these products to have the testing method to be able to say, all right, this you developed this in a lab, and is this what this is supposed to look like? Is this, does this come out to meet the standards that exist, and the authoritative bodies out there that are there to enforce the standards? It's one thing to have a standard written. It's another to have a verification that the product meets those standards. And I'm sure, John, you've seen quite the variations, like you just said, not just on the fire product, but on other products as well. Even in the development of things, like you said, it can be the slight change or the inclusion or not in the manufacturing process that can change a lot about the product. So I think it's a very worthwhile topic for us to talk about, and I think maybe something that will, as we continue to have these sort of mini podcast episodes, something to talk a little bit more about what went into that testing. I've certainly enjoyed the conversation around the chemistry and things, and hopefully one day we can have a graphic design team that can help us, illustrate all of the molecules and the bonds and molecular chains of these products, so that we can visualize them. I know I've sat down with Steve a number of times, and he'll pull out a notebook and he draws and says, this is how this is, bound together, and you move it over here and now it performs in a different way, and all that stuff is super interesting to me. I'll sort of wrap up and open up for any kind of closing remarks for you guys. But this whole topic is around the expertise that we have in our toolbox, and the great service that you help us with, John, and understanding this chemistry, and likewise many other technical advisors that we have. But that we are still here to help understand and solve challenges and problems that a current customer or a future customer may have, and that we're expanding the capabilities of our team and continuing to provide this guidance and this consultancy for information and support to our customers. And so we welcome anyone who's listening to this or may come across our website to please reach out to our sales team, reach out to our technical team. And as we add more information to our website, that'll be readily available with any questions that you have. We want our markets, our customers and potential customers to be as informed and as knowledgeable on this information as possible, so that they can make the best informed decision at the end of the day. Anything you guys have to add to that?
John?
No, not really. I mean, I do enjoy working with Standard Fluids, consulting for them. They're really one of my principal clients, and they are by far the organization that makes the best use of a lot of the compounds I'd worked to help develop in my career. So it's really rewarding to see them help industries still maintain operations and do it in an environmentally responsible manner.
Yeah, I mean, I just want to close with one detail. I remember when we started Standard Fluids back in 2023 over there in Chicago. I remember that John was consulting with us. We were asking, what do we want to do? What can we improve? And if I'm not mistaken, else we can correct me if I'm wrong, John. I think you brought up that you wanted to change part, or you wanted to modernize or optimize the process of quality checking or the purity checking of the process, like to make it not exactly as we were using, but optimizing in some sorts of way. Now that we're Standard Fluids, and and that's one of the things that we are the same team that brought and invented the product and developed it through the years. We were also looking, and we're also constantly looking on ways on how to improve our processes, improve our delivery, improve our service, and be more flexible and open to being able to reach out to the customers that we have abroad. And as mentioned here in this meeting, in this podcast, we have nothing less than John Owens. One side we have Paul Rivers. We have Steve Pignato in our team, and others that help us to achieve this. And I'm really humbled to be part of this team. I'm really proud of being part of this team, because it's been amazing for me as a professional to have lived and developed my career amongst such great people.
Yeah, I echo that exactly, Kelvin. You've had the privilege of working with these amazing people prior to Standard Fluids, and being able to be a part of what we're creating now is it's very fun and exciting to be able to be a part of this. And just like what John said, it's amazing for us to continue to show the value of the products and the value of the work that you dedicated your career to, and continue to do these things. So we appreciate your continued support. And that this is where we continue to appreciate the support of our customers and the markets that we serve, for coming to us for guidance and support. That's where we really we get the most enjoyment out of, is being able to solve a problem, provide some guidance, and remind people that this expertise is built on decades of experience and the most intimate knowledge of these products. You can't get it from anyone else. This is the team to get it from. And so anyone listening, please reach out to us with any questions. Get in touch with us. We've got a great team of people ready to talk to you and help you out, and help us solve some problems. We look forward to it. And likewise, in these forum and discussions, if maybe you're a little shy and you don't necessarily want a sit down conversation with Kelvin's friendly face or anyone else on our team, send us a suggestion for a topic that you want us to discuss in these podcasts. This is a more public forum that everyone else can hear and get some insight as to what things are going on within Standard Fluids and what we're doing. So suggest some topics to us. But with that, we'll go ahead and wrap up Splashcast episode 5. Thank you very much, John, and thank you very much, Kelvin, for taking the time out of your week to do this. As always, Standard Fluids, we are the solutions that you need from the people that you can trust. And so please reach out to us soon, and we'll see you all on the next episode. So thanks, guys.
Got questions?
Thanks, Nolan.
We got answers.
Yes. Thank you very much, guys.
Thank you very much.